Hello, this is Elder Tehila from the Coven of the Open Mind, and you're watching Metaphysics 101. Hail and welcome. So the topic this time is on general relativity. If you recall from the last video, we spoke about special relativity, which describes the nature of physics based on the fact that light always moves at the same speed. So the metaphysics principle we learned from special relativity is that objectivity does exist in this universe, even though subjective truths also exist and can be contradictory. General relativity is a description of the laws of gravity based on the observed behavior of light. First, let's talk about what gravity is. Gravity is the attraction between two massive objects. For instance, the solar system, the Earth orbiting around the sun. The Earth orbits because it's attracted to the sun, but it doesn't fall into the sun because it's moving fast enough in one direction that it's just always falling. That's what an orbit is. When a spaceship is in orbit around a planet, that means that it's always falling. The people inside of the spaceship are floating around because they're always in a state of free fall. How gravity is generated, essentially there's a field in our universe where a field is just energy that we call the Higgs field. As certain kinds of particles move through the Higgs field, they're given mass. Essentially, they slow down at different rates depending on what kind of particles they are. That's a really simplified way of looking at it, but that's where mass comes from. So some particles don't have any mass at all, like photons. Light has no mass. It doesn't attract any massive things to it. Humans have mass, the Earth has mass, pretty much everything that physically exists has mass. One of the only exceptions to that is photons. Some things are so light they appear like they don't have mass, like electrons, but they do actually have mass. It's just that they're so light that gravity is not a very significant force in their lives. Electrons care far more about other fundamental forces, which will be the subject of later lectures, than they do about gravity. So when gravity becomes important is when you're talking about big objects, celestial objects like planets and stars and black holes. Black holes are really cool, and we're going to talk about them in depth, what they are and why they're important to physics and to metaphysics in this video. If you remember from the first video, we said light does not change speed. That's something that we've measured to be the case, that we can justify using mathematics and science. Light always moves at the same speed. This creates all sorts of weird phenomena like time dilation and length contraction. We talked all about that in depth in the first video of this series. In this video, we're going to talk about what it means for light that it can't change speed as it moves around massive objects. Remember from the first video that we talked about the relationship between energy, mass, and momentum. Even though photons don't have mass, they do have momentum. They're always moving. If photons weren't always moving, then they would have no energy, and nothing has no energy. Even empty space in a vacuum has energy. Momentum is the velocity of an object, essentially how fast an object is moving. When you're in space and there's no air to slow you down, there's no friction, there's nothing to cause something to stop moving, it just continues moving forever. An object in motion stays in motion unless acted upon by an outside force. That's one of Newton's laws of motion that is very true even for objects moving close to the speed of light. So if an object is moving through space, what external force could act on it to cause it to change its momentum? Massive objects. Let's say that a rock is floating through space like an asteroid, and then another rock that's floating through space comes close to that asteroid. Well, those two objects are massive, so they will attract each other. And that will mean some kind of force exists between them, causing them to move together. The attraction between these two objects is no different than the attraction between you and the Earth. The Earth is rotating around and around very, very fast. We know this because The moon rises and sets, and the sun rises and sets, and all of that happens because the Earth is itself rotating. If the Earth is rotating really, really quickly, then why don't we all fly off? Well, we don't fly off the Earth because we are attracted to the Earth. The Earth is massive. We are massive. Therefore, the Earth is exerting a force upon us that forces us to stay put, that forces us to be firmly planted on the ground. If the Earth were less massive, then the amount of force keeping us on the Earth would be lower. For instance, when people go to the moon, they can jump really high. That's because the moon is less massive than the Earth. So it exerts less of a force on the people that are on the moon than the Earth does for the people that are on the Earth. We are constantly accelerating towards the center of the Earth, and the ground prevents us from moving towards the center uncontrolled. That's why if a spontaneous sinkhole develops, all of a sudden everything falls in toward the center of the Earth. So even if you accelerate an object up, the Earth is always exerting an acceleration down. That's what causes things that go up to come down. Now, what happens if we say, get in an elevator? Well, the elevator has to exert enough force upward that we're overcoming the force of gravity. Or if we walk upstairs, we have to exert an additional amount of force in order to overcome the attraction that we feel towards the Earth and allow us to go up. Just like how a ball sitting in your hand is not going to fly up into the air, you have to throw it. You have to give the ball an upward acceleration if you want it to move away from the Earth. If you just take the ball and drop it, it's never going to go up and then down. It's always going to go straight down. It will always experience an acceleration down towards the Earth, and moving it up above its starting location requires a force that is contrary to the force of gravity, which is always pushing down. So let's say you're in outer space and you're moving at a constant speed. Okay, well now you're going to just float around inside because there's no gravity to hold you on any surface of the ship. There's a small amount of gravity between you and the walls of the ship. If you just were sitting in the middle of the ship and you never moved, you would very, very slowly move toward the walls of the ship. But all of the walls exert a force upon you. So if you're perfectly in the middle of the ship, which wall do you move towards? Neither. You would just sit there in perfect equilibrium. If you started a little closer to one side than the other, then you would slowly move towards the wall. But the force of gravity between you and the wall is so tiny that it would be an effect that would take so long to see, you'd be dead before you ever touched the wall. This is in a ship that's moving at a constant speed. There's no acceleration. You're not speeding up, you're not slowing down. Think of it this way. If you're driving on the highway and you're going 60 miles an hour and your cruise control is on, then you're moving at constant speed. You could toss a ball up into the air and catch it, and all of the physics inside of your car will function exactly the same way as if you weren't moving at all. If you toss a ball up into the air and then suddenly slam on your brakes, the ball is going to hit you in the face. Because now you're experiencing an acceleration, or in this case, a deacceleration, which is the same thing. It's a negative acceleration. Acceleration is when you change your velocity over time. So, the Earth is not pulling you towards it at a constant velocity. It's pulling you towards it at a constant acceleration. You are always being pulled downward into the Earth at an acceleration. That means, like I said, if the ground disappeared, you wouldn't stay where you are. You would move towards the center of the Earth. Now, there's no difference between the acceleration caused by gravity and any other kind of acceleration. Here's the spaceship. Here's the back of the spaceship, the butt of it. And here's you floating around in the center because the spaceship is either moving at a constant speed or not moving at all. Now the spaceship starts to accelerate. It starts to move faster. But you're not moving because you're not connected to the walls of it. So you're going to move toward the wall of the spaceship, and then it's going to drag you along with it. If the spaceship were moving at the same exact acceleration that gravity pulls you down to the Earth, then you would not notice a difference between being in a box moving in space and standing on the surface of the Earth. To you, there'd be artificial gravity on your spaceship. In fact, what creates artificial gravity in space stations is the rotation of the space station. So if you've ever been to a carnival, they have that centripetal force ride where you stand and hold on to these bars. And you don't even need a real seatbelt because once it starts spinning, it pushes you to the outside. If it pushed you to the outside strongly enough, then you could stand on the walls of this circular ship and you could walk on the side of this circular ride. You could literally stand up and walk around. And you could walk all the way around it and come back to the start and walk all the way around, and it'd be no different than if you were standing on the ground of our planet. Artificial gravity in spaceships is created by rotational motion, an acceleration that pushes you to the outside of the ship, which is what forms the ground. So now you take a person and you knock them out and they're sleeping and you put them in a box, and then you shoot that box in outer space. And then you have that box accelerate in outer space at the same rate that gravity accelerates us toward the center of the Earth. They might not even know that they are in space. If there's no windows inside that box, there's no way for them to tell they are in space. The physics inside of that box would be exactly the same as the physics on the surface of the Earth. It's a very cruel prank. You can create what seems like gravity just by accelerating a person through time and space. So now let's return to talking about massive objects in space. On the surface of the Earth, there is nothing massive enough to cause light to bend. If I shoot a light beam in one direction, it's going to keep moving in that direction until it hits something and then is retransmitted or reflected back to me. If it's a reflective surface like a mirror, it'll just be reflected. And if it's an object like the wall or a plant, it'll be absorbed and then retransmitted at a certain wavelength, which is how we see color. On the surface of the Earth, all light will pretty much move in straight lines. The shortest distance between 2 points is always a straight line. However, in space, that's not always true. The physics of the astral realm is different than the physics of our physical realm. If an object is really massive, then the shortest distance around that object might not be a straight line. This is because as the light moves past a massive object, it will lose energy. Remember, energy and mass are intimately related. E equals mc squared, right? So if something is losing energy, that means it's losing mass. But light doesn't have any mass. So what is light losing? That's why you need the extended equation that relates both mass, energy, and momentum. Light can't lose mass, so it has to lose momentum. But it can't lose momentum either because light never changes speed. So when light slows down, what really happens is a time dilation effect. Because light always moves at the same rate, it has to have a lower frequency at the top of the cliff than at the bottom, just like we said in the last lecture. The amount of wavelengths you see in a period of time are lower as the light moves away from Earth. It changes color. It red shifts because it's losing energy. But it has to move at the same rate and it has to have the same mass, which is nothing. So what this means is, if a light beam is moving past a massive object, it's going to experience time more slowly while it's passing the massive object. So now, for the light beam, the shortest distance between 2 points is not a straight line, because in the middle here, it's slowed down. It's not moving slower, but time is literally passing more slowly in that region. So what happens is the light beam curves around the massive object, and that allows it to experience time at the same rate the entire time. Because light can't slow down its speed, it bends around massive objects. This is an effect called gravitational lensing. It's one of the ways that we can identify how massive a galaxy is, because as light bends around it, we can measure the effect of it being bent and then determine how massive the galaxy must be in order to bend it. So you can think about the universe, you can think about space-time like it's a taut blanket. And when you place a massive object on it, it forms a hole or a drop towards where the massive object is located. So if I place less massive objects around it, the less massive object, say a marble, is going to roll toward the larger ball, because now there's a force accelerating it in that direction. If I take a marble and I shoot it past that massive object, well, it's going to move towards the object, or it's going to go up and around and go past the object. For most massive objects, we're not talking about a true hole, something that's like bottomless, okay? There's always going to be a bottom in this hole, something to collide with, unless it's a black hole. Black holes are massive objects in space, but the mass of them isn't the most interesting part. The interesting part is the density. Density is how much mass you have concentrated into a small area. If we're talking about a person and we're saying that a person is really dense, then what we're really saying is that the amount of strength they have based on the amount of muscle you actually see is really high. They don't appear to have strong muscles, but they're really strong. So you'd say that their muscle density is really high. Well, the same thing works for objects in space. If something is really dense, then it's a lot of mass taking up not a lot of space. The Earth is massive, but it takes up a pretty large amount of space, so it's not that dense. The Sun is massive, but it takes up a huge amount of space, so again, it's not that dense. A black hole is something way more massive than even our Sun, and it's taking up a space that is smaller than the space of the Earth. In fact, it's postulated that black holes are infinitely dense. They say that in the very center of a black hole there would be what's called a singularity, a point that is infinitely dense. We don't really know that much about what happens inside of the center of a black hole because we can't see it. Black holes are so massive that even light cannot escape them. If light falls into a black hole, then nothing can escape. We can't see what goes on inside what's called the event horizon. So a black hole would be like a tear in space-time, a literal bottomless pit that everything falls into, and once it gets past a certain point, nothing can escape. There's no amount of acceleration large enough to get something out of a black hole. This is because the acceleration due to gravity increases as you move closer to the singularity, or the point at the center of a black hole that is infinitely dense. Black holes are so massive that as things move into them, they become elongated, they get stretched out, they get torn apart by very strong forces, turbulence. This leads us to ask the question, what happens to light? If light has to always move at the same speed, and it can't accelerate as it falls into a black hole, then as light moves into the black hole, that light must be experiencing time more slowly the closer it gets to the center of the black hole. Inside of a black hole, time would completely stop. We have no idea what it looks like past the event horizon, because once something falls past a certain point, nothing can escape. Nothing can move fast enough to get away. Nothing can move faster than the speed of light. So if light can't even get away, then certainly an instrument measuring what happens couldn't get away. That's why they're called black holes, because we can't see into them. They look black, except sometimes when they have energy pouring out of the edges of them, which is called Hawking radiation. It becomes very complicated. If someone were to fall into a black hole, they would move slower and slower and slower, and they would basically move infinitely slowly, and you wouldn't be able to even see them fall in because they would appear to just stop to you on the outside. The relevant takeaway here is that massive objects literally change the way that things move through space and time. They can be thought of as changing the shape of space-time itself. We like to think about the universe as being this static, three-dimensional place where things move around like in an RPG, where everything is separate from each other and is almost hung up, like how you could create a solar system model by tying the planets to strings and hanging them all from the ceiling. In reality, space-time is not static. As massive objects move through space and time, they literally change the shape of space and time, which changes the way that light behaves and the way time passes. It changes the way time behaves. If someone were to accelerate a ship to the speed of light, or close to it, because remember, you can't move a massive object at the speed of light because it would become infinitely massive. It would become a black hole. If something were to accelerate rapidly close to the speed of light, then you would find that the laws of physics would change around it. Time would pass more slowly. Things would fall into it or fall away from it at different rates. This is what's called background independence. The fact that the physics of gravity can change the shape of space-time, can change the way physics behaves for other objects within space, means that gravity is not a force that exists on a background. It's not an actor on a stage. Because gravity exists, the nature of the stage is constantly changing. This means that fields of energy that exists within space, are not just playing out. Space and time acts like a field itself. By itself, it is in flux. It's changing. This means that there is no general sense for energy conservation over individual parts of space, but over all of space, energy must be conserved. If something falls into a black hole, something has to come out of the black hole in order to ensure that energy is conserved. What this tells us is that things can cease to exist. Energy can be wiped out of existence. In a background-independent environment, energy doesn't have to be conserved. Over all of space, it does. But over an individual part of space, it doesn't. Something could fall into a black hole and cease to exist. The black hole has to radiate some kind of energy in order to counterbalance the sudden lack of existence of this physical thing. But the energy of this one particular thing does not have to be conserved. The energy coming out of the black hole could be something else entirely. Things can cease to exist. That's what general relativity tells us. Likewise, the nature of the background independence of general relativity becomes incredibly significant when we talk about quantum mechanics, which is the next lecture. Quantum mechanics is background dependent, and all particle physics is. Reconciling the background independence of general relativity with the background dependence of quantum mechanics has very interesting consequences and tells us a lot of really interesting things about the universe. And that's where the metaphysics gets cool. So for now, walk away from this lecture knowing the universe is not background dependent. Space and time are changing all the time. The stage upon which all of these celestial bodies interact with each other physically changes. The physics of space, of this astral realm, is very different than the physics that we see on the surface of the Earth. Time can and will move at different rates, depending on what massive objects are located where in space. If you walk away from this video knowing nothing but background independence, that's good. Space is background independent, it's in flux, it's always changing, and this has a lot of consequences that we'll discuss in the later lectures. I hope all of this made sense to you. If you have any questions, please feel free to drop a comment here on this video or to email us at covenantoftheopenmind@gmail.com. I hope the interesting nature of the astral realm has now been made very clear to you guys, and that we can move on from here knowing that things get even weirder. From all of us here at the Covenant of the Open Mind, blessed be.